All right, now section 5 of chapter 6, talking about integration by substitution. So we got several things we want to cover in this section. We want to use pattern recognition to find an indefinite integral, use a change of variables to find an indefinite integral, use the general power rule for integration to find an indefinite integral. Noticing a pattern there. Anyway, use change of variables to evaluate a definite integral and evaluate a definite integral involving an even or odd function. So let's get going on this. Let's start with pattern recognition. So one of the key things that we want to be able to do is identify a pattern when evaluating integrals, whether they're indefinite or definite integrals. So we're going to study techniques for integrating composite functions. And the discussion splits into two parts, pattern recognition and change of variables. Both techniques involve a U-substitution. This is closely related to the chain rule. With pattern recognition, you perform the substitution mentally, and with change of variables, you write the substitution steps. So I'm going to recommend that you almost always write the substitution steps because it can get complicated quickly and you can lose track of what's going on in your mind. So the role of substitution and integration is comparable to the role of the chain rule in differentiation. I like to refer to this loosely as the reverse chain rule. So recall that for differentiable functions given by y equals f of u and u equals g of x, the chain rule states that the derivative of a composite function f of g of x is the derivative of the outside evaluated at the inside multiplied by the derivative of the inside. Well, from the definition of an antiderivative, it follows that if you integrate f prime of g of x times g prime of x dx, you should get capital F of g of x plus c. Should be that pretty much that straightforward. So these results are summarized in the following theorem. This is the antidifferentiation of a composite function theorem. Let g be a function whose range is an interval I, and let f be a function that's continuous on I. If g is differentiable on its domain and f is an antiderivative, capital F rather, is an antiderivative of little f on I, then the integral of f of g of x times g prime of x equals capital F of g of x. Letting u equal g of x gives du equals g prime of x dx. It's kind of like solving for the differential of du. And you could rewrite this as f of u du. So the integral of f of u du is capital F of u. So this is kind of like the reverse chain rule right here, and this is using U-substitution. Now I know that might be kind of abstract just looking at it there. So what we'll do is go through a couple examples. So example 1 is going to show how to apply this theorem directly by recognizing the presence of f of g of x and g prime. Note that the composite function in the integrand has an outside function f and an inside function g. So there's an inside function here, an outside function here. Also, the derivative of g prime, is present as a factor of the integrand. So let's find these two indefinite integrals using this pattern recognition. So in the first one, notice that you have an inside function here, x squared plus 1, and the outside is squared. And then you have multiplied by another factor here. So let's see if things line up. If you let g equal x squared plus 1, the inside, then g prime is 2x. It's right there. So you have f of g of x equals f of x squared plus 1. X squared plus 1 is the inside of the squaring function. So it's x squared plus 1 quantity squared. From this, you can recognize that the integrand follows the f of g of x g prime pattern. So you have your f of g of x here, your x squared plus 1 is the g of x inside f, which is the squaring function, multiplied by the derivative of g. So that's like the answer to the chain rule problem of the derivative of 1/3 x squared plus 1 quantity cubed. So the integral is equal to 1/3 x squared plus 1 quantity cubed plus c. So if you try using the chain rule to check that the derivative of that is the integrand of the original integral. So if I do that, you have 3 times 1/3, cancels those, then you have x squared plus 1 to the second times the derivative of the inside, which is 2x, and the plus c would go to 0 because that's understood to be a constant. And we're good. Alrighty. So if you didn't completely understand that, you might want to rewind and watch it again. But as we do a couple more examples and you try a couple on your own, things might start to click a little bit more. So problem B, if I go back here, is the integral of 5 root 5x plus 1. So it's the integral of 5 root 5x plus 1 dx. Let me just write it there. So notice that 5, if I let g equal 5x plus 1, that's the inside of the square root, the inside's derivative is present as a factor of the integrand. So if g is 5x plus 1, g prime, is 5. And f of g of x equals f of 5x plus 1, which is the square root of 5x plus 1. You could rewrite it as the 1/2 power. So, oops. Don't know what happened. Oh, I just had things out of order a little bit. From this, you can recognize that the integrand follows the pattern, f of g of x, g prime pattern. So use the power rule for integration in the theorem to write the integral of 5x plus 1 to the 1/2 power times 5x. Reverse the chain rule, so you would add 1 to the exponent, multiply by the reciprocal, add your plus c. So you get 2/3 times the quantity 5x plus 1 to the 3/2 power there. So let's back up. So for this one, I want to find the integral of x times the quantity x squared plus 1 quantity squared. So if you'll notice, you have an inside here, so like your g would be x squared plus 1. Now g prime is equal to 2x, which almost fits, except you're missing the 2. So what do I do? Well, so this is similar to the example in 1a, except the integrand is missing a factor of 2. Because 2x is the derivative of x squared plus 1, you can let g equal x squared plus 1 and supply the 2x in this way. So if you multiply by 2 and divide by 2, or multiply by 1/2 and 2, those would essentially cancel each other out. But the reason we do that is so that we get a factor of 2x in the problem. You do have an extra factor of 1/2 multiplied in there, but you can just move that to the front of the integrand, or the integral, like this. So now I have the form f of g times g prime. I can reverse the chain rule, so you add 1 to the exponent, which becomes 3. The 2x, I like to think of it as it like kind of goes back in. Remember how you multiply by the derivative of the inside? So you kind of just kind of goes back in is how I kind of think of it. So you'd have x squared plus 1 quantity cubed over 3, or times 1/3, times the factor of 1/2 that was factored in. And you end up with 1/6 x squared plus 1 quantity cubed plus c. Now, an important thing is you can adjust for the constant. Like if you're missing a factor of a number, a factor of a constant, you can multiply or divide to adjust for that. However, if you're missing a factor of a variable, you cannot multiply or divide out a factor of x or x squared or anything like that. Like in this integral, this almost looks like it would work, except you're just missing a factor of 2x. Well, you can't multiply and divide by 2x because now you're introducing other variables, and that's not a legitimate way to adjust. We'd have to do something else, and this integral right here is beyond the scope of what we're going to do right now. So remember, you can adjust for a factor of a constant, but not a factor of a variable. Might have to do some other things. All right, and we already went through that. All right, the integrals in example 1 fit the f of g times g prime pattern exactly. You only had to recognize the pattern. So you can extend this technique considerably with the constant multiple rule. So if you could factor out constants and multiply constants like we did in example 2. And many integrands contain the essential part, the variable part of the g prime, but are missing a constant multiple part. In such cases, you can multiply and divide as necessary by the necessary constant multiple. All right, so that's it for pattern recognition. Stay tuned for the next video.